Welcome to the Walton Pi. Today we're going to be talking about strategies for integrating, or you might refer to it as the order of things to try when you got no idea what is going on. So before we can jump into strategies for how to integrate different integrals, we need to start with a solid foundation in knowing the antiderivatives of several elementary functions. So we're going to go through these antiderivatives first and then jump into different strategies. So to start off, the integral of x to the n is x to the n plus 1 over n plus 1 as long as n is not negative 1. If n is negative 1, then that's the same thing as saying the integral of 1 over x, which is the natural log of the absolute value of x. The integral of e to the x is e to the x. The integral of b to the x, where b is some other positive number, is b to the x over the natural log of b. And then we have the integrals of our trig functions. So the integral of sine x is negative cosine of x. The integral of cosine is sine. Integral of secant squared is tangent. The integral of cosecant squared is negative cotangent. The integral of secant times tangent is secant. And then the integral of cosecant times cotangent is negative cosecant. If you have the integral of secant, this is the natural log of secant x plus tangent x. The integral of cosecant x is natural log of cosecant x minus cotangent x. And so if you come across any of those, these are ones that are useful to remember because they're not that easy to figure out when you come across them. Integral of tangent is the natural log of secant. The integral of cotangent is the natural log of sine. These are not as important to remember because these are doable using u substitutions. And then if you ever come across these hyperbolic functions, remember that the integral of sinh, or the integral of hyperbolic sine, is hyperbolic cosine, or cosinh, and then the integral of cosinh is sinh. So now that we've gotten all of those done, let's go right into our first strategy. So if at all possible, try and simplify the integral. So for example, the integral of tangent times cosine. This is not one of the forms that we saw earlier. However, if we rewrite tangent as sine over cosine, the cosines will cancel. So this is just the integral of sine, which is negative cosine plus c. And so if you're able to simplify. It might make it a lot easier to be able to go through and do. If simplification didn't get us to the point where we were able to integrate it, the next thing that I would probably try is to see if there's any obvious substitutions where the derivative of that substitution also appears. So try and see if a u substitution is going to work. So, for example, the integral of x squared plus 2x all over x cubed plus 3x squared plus 7, there's not any simplification we can do right here. But if we say that u is the bottom, the derivative of the top is 3x squared plus 6x, which is pretty close to the top. It's just 1/3 of the top. So we can say that the top can be replaced with a 1/3 du, and the bottom can be replaced with u. So this is just 1/3 the integral of 1 over u du. So this is 1/3 the natural log of u, which is 1/3 the natural log of the absolute value of x cubed plus 3x squared plus 7 plus c. So if simplifying by itself didn't work, try u substitution. That might work. Sometimes u substitutions don't work. And if that's the case, the next thing I try is integration by parts. So it's one of the most powerful ways to be able to compute an integral. And it might be helpful to remember that there's really only two ways that we can find the integral of something. It's either a u substitution or integration by parts. You just kind of have to figure out which of these is it. Sometimes it's pretty complicated to figure out exactly what the substitutions are, but your choices are basically substitute or integrate by parts or approximate the integral. So if you couldn't figure out a u substitution, try integration by parts. So if we can make clever choices for u and dv, we're able to rewrite the integral as the sum of two different functions, and hopefully it's a way that we can be able to integrate. I say hopefully because it's not always going to work out super nice, but hopefully it's going to give us something that'll work. So if we're trying to decide if integration by parts would be useful to even try, there's a few things that we can keep our eyes out for that help us make educated guesses for what to make u and what to make dv. So first, if there's a logarithm anywhere, make the logarithm and whatever's inside the logarithm be your u, because it is so much easier to take the derivative of a logarithm than it is to try and integrate it. So that's my general rule of thumb. Take the thing that's easiest to integrate and make that dv. Whatever else, you can take the derivative of just about anything using the product rule, the quotient rule, the chain rule, and so on. So if you have no idea how to integrate a piece that's inside the integral, make that u, and then hopefully that complicatedness will disappear pretty quick. If you ever have a polynomial inside, setting that to be u is often a wise choice. The only main exception that really comes up is if it's a polynomial times a logarithm. You want the logarithm to be u, so then the polynomial would be your dv. But in general, a polynomial as u is usually going to work out nicely. If you ever have e to the ax, so e to the something, that's easy to integrate. So make e to something x as your dv. That'll usually work out nicely. And then if you ever have sines or cosines, those can usually be either the u or the dv. So we usually make them the dv unless there's an e to the ax, but they're able to go just about anywhere. So that's my general rule of thumb that I look for when trying to figure out what should I do for my u and what should I do for my dv. There are other types of integration by parts, but these are the most common ones. And so these are the sort of general rule of thumbs that I've developed and I'm sharing with you. So the last thing to remember with integration by parts is to not be scared if you have to do integration by parts twice or 3 times or 4 times, because integration by parts does reduce the complexity usually, but you might have to do it a few times to be able to evaluate it before you get to an integral that you can solve, or other times you might do it a few times and then have your original integral pop out again. And if the original integral ever pops up again, solve for the integral. Treat the integral as one thing and then move it and manipulate it algebraically to one side to then be able to solve for it. So for example, let's say that we have the integral of e to the 2x times sine of 3x dx. Now, let's use our general rule of thumb. We have an e to the something and we have a sine to the something. So e to the something, let's make that dv. So we're going to say dv is e to the 2x dx, which leaves sine of 3x to be our u. We could have chosen dv to be sine of 3x dx and then v to be e to the 2x. Both methods would work. This is just the method that I chose. So if u is sine of 3x, then du is 3 cosine x, or 3 cosine of 3x dx, and v is going to be e to the 2x over 2. So the integral of u dv is uv minus the integral of v du. So we got sine of 3x times e to the 2x over 2 minus e to the 2x over 2 times 3 cosine of 3x dx. And so that can be rewritten as e to the 2x sine of 3x all over 2 minus 3 halves the integral of e to the 2x cosine of 3x dx. Now, this we're going to do another integration by parts. This time u is cosine of 3x, dv is e to the 2x dx, because e to the something, really easy to integrate. So we got v is e to the 2x over 2, du is negative 3 sine of 3x dx, and so plugging that in gives us this. Now, this is a bit messy, so let's distribute everything through and rewrite this integral. So this gives us an e to the 2x sine of 3x over 2 minus 3 cosine 3x e to the 2x all over 4 plus a negative 9/4 integral of e to the 2x sine of 3x dx. Well, looks like we're going to have to do integration by parts again. Unless we notice that we have e to the 2x sine of 3x inside an integral on both sides of our equality. So we can add 9/4 of the integral e to the 2x sine 3x dx to both sides, and we are left with 13/4 the integral of e to the 2x sine of 3x dx equals the right-hand side. So to solve for e to the 2x sine of 3x dx, or the integral of that, we can multiply both sides by 4/13. And when simplifying, we get this. The integral of e to the 2x sine of 3x dx is 2 e to the 2x sine of 3x over 13 minus 3 cosine 3x e to the 2x over 13 plus c. So that's how we might be able to use integration by parts to solve this integral. The fourth strategy that we can come across is if we ever have a polynomial divided by a polynomial, I usually, if U substitution doesn't work, I jump straight to partial fraction decomposition. Now, I know it's not the favorite method for a lot of people, but it is very useful and very powerful because it can reduce the integral to the sum of several simpler functions or fractions, which we can then try and integrate. So for example, the integral of x cubed plus 3 over x minus 1 times x plus 1. Well, first, this is not a proper rational function, so we are going to do polynomial division, and that gives us x minus 1 plus something over x minus 1 times x plus 2, and partial fractions will give us that those values on top of those fractions are 4/3 and 5/3 respectively, and this integral is so much easier to integrate. We can integrate x, we can integrate -1, we have 4/3 over x minus 1, that's a simple U substitution, 5/3 over x plus 2, that's also a simple U substitution, and so this is something that's now doable. The fifth strategy that I would do is if you ever see the square root of x squared minus 1, x squared plus 1, or 1 minus x squared, then we can likely use a trig substitution to rewrite the integral. Now, this will work also in some situations where it's not a square root, but in those situations, often a U substitution can also work. However, if those aren't working or you're not seeing how you can do it, try a trig substitution if it's one of these three forms. So if you ever see the square root of a squared minus x squared, make the substitution x equals a sine theta. If you ever see the square root of a squared plus x squared, say x is a tangent theta. And if you ever see x squared minus a squared, then x is a times secant theta. So, for example, the integral of dx over the square root of 9 minus x squared, that's, if we say x is 3 sine theta, that gives us dx becomes 3 cosine theta d theta. So we got the integral of 3 cosine theta d theta over the square root of 9 minus 9 sine squared theta, which becomes 3 cosine theta over the square root of 9 cosine squared theta, which becomes 3 cosine theta over 3 cosine theta. So we're just integrating 1, so that just gives us theta plus c, but then theta is inverse sine of x over 3. So that means that the integral of dx over the square root of 9 minus x squared is arc sine of x thirds. That's how we're able to do trig substitutions. So these are useful and would be ones that I would recommend keeping in your head and trying to recognize anytime you see x squared minus a constant, x squared plus a constant, or a constant minus x squared, try a trig substitution. The sixth strategy I would do is to try and see if you have trig functions, so like powers of sine times powers of cosine. There's a few common techniques that we can use. So if the power of cosine is odd, replace, and we are dealing only with sines times cosines. If the power of cosine is odd, replace all but one of the cosines using the identity cosine squared x equals 1 minus sine squared x, and then make a U substitution of u equals sine x. This will simplify the integral quite a lot. It'll turn it into just the integral of a polynomial. So for example, if we have the integral of sine to the fourth x cosine cubed x dx, this has an odd power of cosine. So what we are going to do is we are going to keep one of the cosines and replace the others with 1 minus sine squared x. So the cosine squared x became a 1 minus sine squared x. And now we can make the substitution u equals sine of x. So this becomes the integral of u to the fourth, 1 minus u squared du, which becomes u to the fifth over 5 minus u to the seventh over 7 plus c. So this is just sine to the fifth x over 5 minus sine to the seventh x over 7 plus c. That's how we're able to integrate this. However, if we have an even power of cosine, but then the power of sine is odd, we're going to do the same thing. Replace all but one of the sines using the identity sine squared x equals 1 minus cosine squared x, and then make a u substitution of u equals cosine of x. Now, if both sine and cosine are odd, you can use this or the last method, or you can substitute either the sines or the cosines. I recommend substituting cosine squared for 1 minus sine squared, because then there are fewer negatives that are going to pop out, and so you are less likely to make a sign error there. However, both methods will work. So if we have the integral of sine to the fifth x cosine squared x, This is sine x times sine squared x squared times cosine squared x dx. Replace all the sine squareds with 1 minus cosine squareds and leave that 1 sine x alone. And so this becomes 1 minus u squared squared times u squared du. And notice that I forgot a negative sign. We forgot a negative sign right here, because if we say u is cosine of x, du is negative sine x. So there should be a negative sign right here, and then this negative sign is going to be missing everywhere else in here. So what I was saying earlier about recommending to use this substitution when possible, I messed up here. We need the negative sign in front of that integral, and I forgot it. So anyway, pretending that there is a negative sign in front, what we are able to do is we can go through the process. This becomes the integral of something, and so we get this, except it's wrong. We need a negative sign in front of every single one of these. So this should really be negative cosine cubed x over 3 plus 2 cosine to the 5th x over 5 minus cosine to the 7th x over 7 plus c. So what I have here is wrong, and that is why I recommend very, very strongly, whenever possible, make the substitution u equals sine x instead of u equals cosine x. They both work, but as I showed here, you can very easily have the sign error where you can mess up by accidentally dropping a negative. And so that's actually exactly what I did here. So that is why I highly, highly, highly recommend saying u equals sine x whenever possible. Now, if both the powers of sine and cosine are even, we are going to use the half angle formulas to rewrite the integral. So that is where sine squared x equals 1 minus cosine of 2x all over 2, and cosine squared x is 1 plus cosine of 2x all over 2. So if we have these situations where we have even power of sine and even power of cosine, this is the way that you got to go about it. So if we have the integral of sine to the 4th x, this is sine squared x squared. So we're going to use the substitution that sine squared x is 1 minus cosine of 2x all over 2. So expanding that out is going to give us this, 1/4 the integral of 1 minus cosine 2x plus cosine squared of 2x dx. Now, the 1 minus 2 cosine of 2x, that's doable. We can do that right now. But the cosine squared of 2x, we're going to have to use the double angle formula again. So that becomes 1/4 the integral of 1 minus cosine of 2 cosine 2x, because that is something we can do, plus 1/4 the integral of cosine squared of 2x. So for cosine squared of 2x, use the double angle formula again. And so this becomes 1/4 the integral of 1 plus cosine of 4x all over 2. And then we were able to integrate the 1 minus 2 cosine 2x. That becomes a 1/4 x minus sine of 2x. And so all of this expanded is going to turn out to be this. 3x over 8 minus sine of 2x over 4 plus sine of 4x over 32 plus c. That's how we're able to integrate this. It's a bit messy, but that's kind of what we got to do when we have even powers of sine and cosine. There are other substitutions we can make for functions comprised of secant and tangent. They're very similar. So if all the powers of secant are even, keep 1 secant squared x and replace all other secant squareds with 1 plus tangent squared, and then make the substitution u equals tangent. If the power of secant is odd and there's at least one tangent, keep 1 secant x tangent x, and then convert all the other pairs of secant squared x to 1 plus tangent squared x, and then we are going to make the substitution u equals secant x. Actually, we should not make that substitution. We should make the substitution, rewriting that, you can find that tangent squared is secant squared minus 1. That's the substitution you would want. And then in other cases, you might need to use another strategy. I hope this video was helpful in understanding the different strategies and techniques that we can use. Feel free to comment any other strategies that you have in the comment section down below. Please like and subscribe if you haven't already so that I can continue to make these videos. Have a great day and good luck with the rest of your math.